Welcome to the inverse Laplace transformation class. Thanks to the inverse Laplace transformation, we can transform a function in the domain of a complex variable s into a time domain function. There are several different methods for determining the inverse Laplace transform, but only one of the methods can be used for any task, so I will focus on only that one. The original function is equal to the sum of the limits, where s approaches the pole's values. The formula looks very complicated, but its biggest advantage is that there is only one formula. But it can only be used if the degree of denominator is greater than the degree of numerator. If both degrees are equal, one must start from breaking function into an integer and a fraction with a lower numerator degree. And actually, the theoretical introduction could be ended here, but I will mention two special cases. If we have poles containing an imaginary part, then we can perform the calculations for only one of the pair of conjugate poles and derive the result as twice the real part. And if we are dealing with a delay t0, we should perform the calculations for the function without delay, and then introduce this delay by simply substituting t minus t0. In a moment, I will show you example solutions for most possible tasks. In the first task, we need to find the original of the function As a reminder, I am pasting the formula we will be using. So our original of the function is equal to the sum of the limits. The function has two different poles, so we will add the two limits together. Let's start with the first limit. The limits tend to the pole's values, that is, to such values of the variable s that the denominator of the function equals 0. A simple equation can be used for this. To proceed with the further calculations, we need to know the pole multiplicity. We can see this by the power to which a particular bracket in denominator has been raised. The pole minus 10/3 has a multiplicity of 1. The factorial of 0 is 1, so we can ignore this fraction. The derivative is I minus first order, so in this case it is 0 order derivative. Therefore, we can also ignore the derivative. Now, according to the formula, we need to write the function for which we are performing the calculations. Then we have s minus the value that the limit approaches. And at the end there is e to the power of st. We write the second limit in a similar way. This time the pole multiplicity is 2. I minus 1 is equal to 1, so this fraction is again equal to 1, and can be ignored. This fraction will only have significance for multiplicity equal to 3 and higher. The derivative of the variable s is of the first order. And inside there is again a function for which we perform calculations. Now s minus the pole value. But this entire bracket should be raised to the power equal to the pole multiplicity. And finally, e to the power of st. And those are all the limits. Now all we have to do is calculate them. But before we go any further, please take a look at what we have written. Inside, in each case, at the beginning, we have the function from the task content. At the end, there is e to the power of st, and in the middle there is such something. And this something has only one task. It has to be reduced with denominator of the first term. If it cannot be reduced, there are only two possibilities left. The first is to extract something in front of the brackets. And if it still can't be reduced, then there is only one possibility. There is a mistake somewhere in the calculations, because that middle factor has to be reduced. If there is only a limit to calculate, one simply should substitute the value into the variable. But in the second component, we still have to calculate the derivative of the quotient. And the derivative of the quotient is the derivative of top times bottom minus top times the derivative of bottom divided by bottom squared. as I said, if only the limit is left, we immediately substitute the value into the variable. We do not waste time on any transformations or ordering. This will be done later. And this is our result. So, such a function in the domain of a complex variable looks like this in the time domain. In the next task, let's assume that the function in the domain of a complex variable is Please note the marking, b of s. The time domain function should be called b of t. The letter should remain the same. Only for functions in the domain of a complex variable we use uppercase letters, and for functions in the time domain we use lowercase letters. In this case, the pole multiplicity is equal to 3, which causes the last element of the formula to appear, that is, this fraction. Denominator should be the factorial of 2, that is 2. Second order derivative with respect to s. This is where an error sometimes occurs, where the bracket is not raised to the appropriate power. Please remember that the bracket from our pole should be reduced in its entirety. I remind you that the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. The content of the task may include information that the result is to be presented as the sum of the components without unnecessary brackets. If so, one will need to get rid of that bracket. And one more task with a higher pole multiplicity. And at this point, I would like to draw your attention to the way the result is marked. Above all, please remember not to leave calculations hanging in the air. Each piece of calculation should be labeled for what it is. So if someone wanted to calculate each limit separately, they could do so, but they would have to mark each limit as another component of the result, for example by using subscripts. But the final result will have to be written separately, in this case as the sum of the previously calculated components. Furthermore, this result must be marked accordingly. If the task content included the command calculate the inverse Laplace transform, the result could be marked as but it could just as well be denoted by However, if the task content includes an information to find the original of the function, or the function in the time domain, it is necessary to mark the result in the latter way, that is, in the case of this task as a of t. Therefore, I encourage you to always use the second marking method, as it will always be correct. In this task, the pole has the multiplicity equal to 4, which means that the fraction will take the value of 1/6, and the derivative with respect to the variable s will be of the third order. One of the most common mistakes in these tasks is forgetting about the remainder after division or determining the incorrect remainder after division. In this case, we have 4 brackets and we need to extract the value 3 from each bracket. Constants can be extracted outside the brackets. A rarer error, but one that also happens, is confusing time t with a variable. The variable is s, so t is a constant. In the next task, we are to determine the original of the function At first glance, the task is very simple, but it should be noted here that we have the same degree of denominator and numerator. Therefore, it is necessary to transform the function from the task content so that the degree of numerator is smaller. There are several ways to do this. I will show one in this task and two more ways in the next task. In the first method, we extract the parameters at the highest power in front of the brackets. Then we write in numerator the same thing as in denominator. But we need to add something else to it to make it mathematically correct. This value is not obvious, so I will use a new variable. And must be fulfilled the equality so the function from the task content is equal to In the next step, I split the fraction into two separate fractions. The degree of denominator is greater than the degree of numerator, so I can apply the expansion theorem, whereas the first component is an integer. The Laplace transform of the Dirac delta is equal to 1, so in the opposite direction, On the one hand, everyone should remember that the Dirac delta is infinity. So 2.5 Dirac deltas are also infinity. But I encourage you to leave the parameter standing next to the Dirac delta. Thanks to this, after calculating the Laplace transform of the result, it will be possible to obtain the function from the task content. On the other hand, if we wanted to use this result further, for example in the simulation, we should remember the integral of the Dirac impulse is equal to 1. That is, the area under the graph is equal to 1. If we have 5-second Dirac delta function, then the area under the graph should be 5 seconds. In the next task, we have to calculate the original of the function again, but with a higher degree of numerator and denominator. Again, we are dealing with equal degree of numerator and denominator. We need to start from multiplication in denominator. Now I will show you another approach to this problem. We look at the coefficients in denominator and how they relate to the parameter at the highest power. The parameter at s has the same sign as at s squared. The value of this parameter at s is twice smaller than at s squared. The last parameter has the opposite sign than the highest power. The value of the last parameter is 1.5 times greater than that at the highest power. Well, one have to add something to make it mathematically correct. Yet another way to determine these first three parameters in numerator is to take the parameters from denominator and multiplying by the ratio of the parameters at the highest powers. It doesn't matter who uses which method, the important thing is not to make a mistake. Now we split the function into two parts. In the next task, we will consider imaginary poles. Let me remind you that instead of calculating the limit for both poles, we can calculate it for just one, but we have to extract two real parts of the result. Here we use Euler's formula. As a reminder, let's draw the unit circle on the side. E to the power of jx is that point on the unit circle. Let's mark the sides of the triangle. This point on the circle can also be written as a real and imaginary part. Sine and cosine of x are but since this is the unit circle, then c equals 1. Therefore, we will use this formula in the further part of the task. We are only interested in the real part, so we ignore the terms that are imaginary. This is quite additional, but I wanted to show that if we calculate the same task, but choose the second of the conjugate poles, we will get the same result. At first glance, the result seems different than before. But just recall the properties of even functions, that is cosine, and the properties of odd functions, that is sine. And finally, we see that the result is the same. Now let's calculate the inverse Laplace transform of the function. The poles are not given, we have to calculate them. Please do not forget about this factor. It is also one of the most common errors. Unfortunately, we cannot proceed with the calculations yet, because we have equal degrees of numerator and denominator. I didn't mention this in previous tasks, but we always have to transform this fraction into a form where denominator disappears. If denominator is an imaginary or complex number, then one should multiply numerator and denominator by the conjugate to get a real number in denominator. And once we have a real number in denominator, we can take it out in front of the real part. However, in this case, it is enough to multiply by j to make denominator disappear completely. I don't know where these errors come from, but lately I often see that if there is a sum in the exponent, some people try to write it like I did here, but they write addition instead of multiplication. E to the power of minus t second is a real number, so we can take this factor before the real part. If the task specifies that the result is to be presented as the sum of the components, without unnecessary brackets, then one needs to multiply it all. And now such an interesting task. It is necessary to find the original of the function a of s even though the poles have a multiplicity of 2, similarly to before, we can perform the calculations only for one of the pair of conjugate poles. Derivative of the quotient, but additionally there is a product in the numerator. If someone has problems calculating derivatives, they should carefully review this area of mathematics. Now let's consider the function with a delay. it is necessary to create an auxiliary function without delay and calculate the original of this function. But again, we have equal degrees of denominator and numerator. And it is a good idea to multiply the entire result by the unit step at this point, so as not to forget about it later. The calculated function d of t is equal to d1 of t, but substituting t minus 2 for time. In the first term, the unit step can be neglected, because the Dirac delta function has a non-zero value only at time 2. If there is e to a constant power in the result, then we should calculate it. And now the last task, also with delay. We proceed in exactly the same way as in the previous task. And that's all I wanted to show you during today's classes. Thank you for your attention and have a nice day.